And I'll introduce you. My attention. Let's just make sure that everything's well.
Do I try to speak? Okay, sure.
And sweet. Can you turn on your camera as well so that
Yeah, sure. It's showing it's already being recorded.
Yes. Yeah, because I can see we can stop. It's already recorded, so that's yeah. Let's wait. Especially
Yeah, the one towards
that's why.
like on to the video side.
So you mean like this door?
No, not the one just beside it. So it came in. Right. So this is what
So this door is unlocked, but that's not
but the one to the right of it.
to the right. Those doors do lock themselves. So, see if I can put it. Hey. Hey. So it's a pigeon. Pigeon. Okay, so welcome everyone. So it's my great pleasure to introduce Baoxiang Wang. So Baoxiang is an assistant professor at the Chinese University of Hong Kong in Shenzhen. And then we actually have the honor of his visit. So he's here for the summer. So anyone interested, in fact, can reach out and then he'll be happy to meet and discuss interesting research. Now, his expertise is multi-agent reinforcement learning. So he'll give us I guess a talk about some of the recent advances that his team has been forming. But generally speaking, I guess Baoxiang is a world leader in multi-agent reinforcement learning. So I guess without any further ado, I'll turn it over to him, and let's welcome Baoxiang.
Thank you. Thank you very much, Pascal. Thanks everyone for joining. So I'm gonna discuss a little bit of mixed motivation interaction between intelligent agents, particularly from the perspective of multi-agent reinforcement learning. So this work is in the intersection of algorithmic game theory and reinforcement learning. So without further ado, let me get started with the problem setting and the introduction. So the talk is based on joint works with Lin Yue, Li Wenhao, and Zhao Hongyuan. They're my colleagues in CU Education. So let's start with some very general, very brief introduction. So reinforcement learning, when we revisit the setting, obviously it has achieved many milestones. But when we revisit the setting, it's basically requiring that the world to be stationary. And for the example, when we have this breakout game in Atari 2600, it's having a stationary reward, it's having a stationary environment. This is how the game is designed. It doesn't change and evolve as our agents are being trained. So in real tasks, in real world tasks especially, so it's usually involving multiple intelligent agents, say multiple humans, where agents are having their own goals. They don't share exactly the same goal. They're also adapting to other agents. Which means from the ego agent's perspective, the environment is adapting. So this introduces the disagreement of real world reinforcement learning tasks to just compared with the canonical setting of RL. So we obviously have a substantial subarea of RL, which is multi-agent reinforcement learning. It does investigate the interaction and influence among multiple rational and usually self-interested agents. So if you ever read papers from Marl, most of them are going to be focusing on two things, which are the two easiest settings. One is fully cooperative, where we have many agents, but they work on the same goal. So in this case, they're pretty much just working on how to collaborate and coordinate among these agents. There's not really a need to just try to influence other agents and just try to influence how they behave, how they adapt to our own strategy. And the other is two-player zero-sum, which is, for example, Go and other games, where, well, influencing your opponent isn't really possible because there's no way they ever listen to you or even just respect your sort of try to influence. So what we're focusing on is actually in between them. It's the mass and less charted field, which is about mixed motive games, where it's not either fully cooperative and not zero-sum. So it's partially cooperative and partially competitive. So talking about influencing others, so if the ego agent in the environment is trying to do something to influence other agents such that their behaviors become more helpful and less harmful. So in computational economics, they have summarized two ways and two only ways. So one is the mechanism design kind of way, which is to provide tangible goods that are like usually just money. So they just buy the other agent's action or policy, so they are helping us a little bit more. And the other is information design. That is, we provide information, we use our information advantage and review part of the information so that their decisions are influenced. So these are the only two ways to directly influence others. There are other indirect ways. For example, you can build a reputation system, you can build infrastructure, and so on and so forth. But today we're focusing on these settings, and in particular, the information design setting. So in general, information design is relatively harder compared to mechanism design if we provide just tangible goods from reinforcement learning perspective, because tangible goods is aligning so much, it's aligning so well with the rewards in RL, which is the succinct numerical this objective that every agent is chasing now. Let me introduce the setting or assumption of this work. So we're assuming that there are agents I, which we call sender, and agents J, we call receiver, and they have partial observations. So there are three things that are required for this setting to happen. One is that there's a communication channel between them. Otherwise, there's no way to reveal information or communicate information. And the other is we have to be mixed motive. It cannot be fully cooperative, where influences are not needed, and it cannot be zero-sum where influences are not possible. And we need information advantage. So if someone is trying to influence the other with information, it has to have informational advantage. So let's move on to that simple example, which is if you were in an information design talk, is probably giving the same example like in the beginning of their talk as well. So that example is like this. We have a bunch of students that are about to enter the job market, and 1/3 are excellent and the remaining are weak. So 1/3 are excellent and 2/3 are weak. So we have a professor. This professor knows exactly each student's quality. The professor knows exactly this student's a good one, that student's a weak one. So it's the information advantage, and the HR cannot know. The HR doesn't know the individual students. The HR only know the prior, which is 1/3 good, 2/3 weak. So, and the professor can communicate with the HR, which means the professor can write a recommendation letter, and it's mixed motive in the sense the professor's goal is to get more students employed, while the HR only wants excellent students, and the HR doesn't want weak students. So to put it numerical, which is, I'm going to put it in the next page, but to put it numerical, basically the professor, when one student gets hired, the professor gets 1 score. And for HR, like good students, 1 score, weak students, -1 score. And the last one is a little bit of assumption. So we assume that the HR knows the strategy of the professor. So it's not really about hiding the strategy. It's about committing to a strategy, a public strategy that isn't exploitable. So here is the chart. So from the, well, in game theory settings, usually we put this kind of chart. So higher, not higher, for HR, it gives 1 and -1. For good and weak students. So not higher is always 0. For professor, if it's a higher, it's just 1. Doesn't matter, it's good or weak. So let's take into 3 examples of this recommendation ladder example. So we can have a professor to reveal no information. And in this case, if the professor reveals no information, both agents are going to get 0 reward. So one thing that we have to emphasize is that there are many ways to reveal no information. For example, if the professor just writes no recommendation letter, then it reveals no information, obviously. Or if the professor simply write a very good recommendation letter for every student, it's the same as revealing no information. So doing any of these, both agents get 0 reward. The reason is that in the prior probability, we have more weak students than good students. So the HR, without additional information, tends to just not hire. So the second one is the professor is just being very honest, and then both agents are getting 1/3 of the reward. Because if the professor is being very honest, then it correctly reviews which students are good and which students are bad. So the HR just hires the good ones, which is 1/3 of them. So 1/3 of the reward for the HR and 1/3 for the professor. So now it comes to the funny thing. So there's a strategy that the professor honestly reports for excellent students. So if the student is good, the professor says the students to be good on the recommendation ladder, but lies for weak students with a probability of 1/2 - epsilon. for some positive ipsilon. For example, if a student is weak, it is possible that the professor just write a good letter instead. Well, this happens with probability 1 over 2 minus ipsilon. So we can think from the HR's perspective. So for a letter, if a letter writes that the student is good, the HR can calculate that it's indeed a higher chance that the student is good, which is a small marginal chance, which is represented by epsilon. But if this happens, the HR does have the incentive to hire this student, so which is called incentive compatible in game theory. So if this happens, the HR buys the story of the professor, and the professor gets 2/3 minus 2/3 epsilon rewards, which is pretty large, right? So if you see the second one, if you see the honest professor, the professor gets 1/3, but for the third example, the professor gets almost 2/3, just 2/3 minus 2/3 epsilon for some very small epsilon. So the third case actually corresponds to information design, and in this case, the optimal strategy of information design. So we read a little bit of the formulation, which is used later. So the formulation of information design from the perspective of the sender, which is the professor, is to maximize the expected utility, which is represented by this WI function, subject to that in the posterior probability of the receiver. Well, this is just the Bayesian posterior. Well, just up to that, we're removing the constant. So under this posterior, the exact action recommended by the professor is actually the optimal action. So which means this professor's recommendation is consistent with the professor's recommendations posterior probability distribution. And in this case, the receiver can be persuaded because from whatever the receiver can see, this is the optimal. And this is what with what the receiver gains a little bit more utility. So this is called the obedience constraint. So in this case, we have the information, the classical vanilla formulation of information design that it just tries to maximize its utility subject to the obedience constraint. So one good thing is, if you see this formulation, it's just linear. Every term is just linear. So if we stop here, we can use linear program to solve it, which corresponds to the early advancements of information design in algorithmic game theory. So what we're trying to do is to try a little bit more to solve more complicated cases. Obviously, this is in very high dimension. We have a for all 8A prime, which makes it super high dimensional, which is actually like the linear program isn't really solvable if you put it into a practical case. So the other thing we wanted to do is we revisit the commitment assumption. So we're saying that the professor is not hiding its strategy. The professor is sort of put it into the public, let the HR know, and commit the strategy without just violating that during the signaling phase. So this commitment perspective is actually from the long-term interaction between two agents. So in the early version, the early proposal of this Bayesian persuasion information design thing, they're arguing that because it's through long-term interaction, so it's more likely that it forms certain kind of stable strategy, certain kind of commitment. So this assumption is making sense. So in a repeated game, what we are trying to do for the second part is we wanted to see if this kind of commitment can emerge through long-term interaction, which is what reinforcement learning is good at. Just a bit of revisit, like why this problem could be challenging from this time from the RL perspective. So one is that it's very non-stationary. is non-stationary in the sense of multi-agent RL is non-stationary, because when you're training your policy, your opponent is also adapting to your policy. And plus that it's non-stationary in the sense when you give more information to your opponent, they are going to take this information immediately, and your information affect their trajectory generation. So if you think about mechanism design, like giving tangible rewards or just money, it doesn't really change the trajectory immediately. It's more like when they revisit, when they're in the end of the episode, they update their policy, it changes their update, but information design changes their trajectory generation. And the last one is how to be persuasive. Obviously, you want your receiver to listen to you instead of to ignore you. Okay, so let's move on to the method part. So we propose a slight adaptation towards MDP, Markov decision processes. So we call it Markov signaling games. So now instead of the state, action, and the next state, which are, well, these are typical in RL, state, ST, action, AT, and next state, ST plus 1. We are having observation, which is consistent with POMDP, partially observable MDP, plus a signaling scheme. So what the signaling scheme does is that apart from the receiver receiving the partial observation O, it also receives a signaling scheme and a signal, sigma, from the sender. So that makes it slightly different from MDPs. And it also obviously involves two agents. So top row and second row, these are done by the receiver and the sender respectively. There are a couple of extensions that I wanted to quickly mention, because one is that I'm presenting all of these without sender's action. So senders only send information, but it is immediate to allow the sender to do action as well. So they can be both in the game. And the second one is on the partial observability. So in the formulation, we're assuming that the first case, which is the sender has full observation to the state, and the receiver has a subset of it. Obviously, it's a proper subset because the sender knows all of the states. So they could be extended to multiple settings. One is that the sender could have only partial observation, while the receiver has a proper subset of that, or they can be just overlapping and not having this kind of subset property, or they can be just not even overlapping, just have completely discrepant information. So our talk only focuses on the first two, and the last two settings are quite hard and are left for future works. So a little bit of notation for assuming that we know a little bit of RL. So we have the state value function, the action value function. So in MSG, we added one more value function, which is the signal value function. So which is the expected value of the sender, conditioned on that our current state is the state S, and our current signal is the signal sigma. And the action value function is the same. So now we have one more value function because we have one more step. And we are representing these as U, W, and V. So with a loss of generality, because we assume that the signal sigma doesn't directly affect the utility, we can have this U as sigma A to be just simplified to W as A. Assuming that it's not depending on sigma directly, condition on that A has been decided. So, yeah.
So I have a question. Here, is there a reason why you treat signal separate actions? Like why can you treat signal as an action? So if we decide as well signal, so it feels like an action. Obviously, it's a special. Why treat it separate?
Yeah, that's a great question. That's exactly what I'm going to put on the next page. Okay. So yeah, we have two lemmas. The first one is the signal ingredient lemma, which is saying that the signal ingredient, which is the gradient of the objective function of the sender with respect to the signaling scheme can be computed as this, which is an unbiased estimation of it. So we have two terms. The first one looks very similar to the action gradient. Well, the second one looks very similar to the action gradient. Well, the first one is actually chaining through the receiver's policy. So if we compared it with policy gradients, which will be the case of treating signaling as taking action, this is exactly what Pascal just mentioned. So if you treat the signaling just as action, what's going to happen is that you get this policy gradient. Basically, this phi, the signaling scheme, will be treated just as the policy of the sender. And so it's basically just the value function, then dot just the score function. So if we compare equation 4 and equation 3 in the signaling gradient lemma, so the second term actually remains almost the same. The only difference is that we have this Q function, which is the signal value function, instead of the W function, which is the action value function. But we're actually missing one term, which is the term that chaining through the receiver's policy, which is actually critical to address the non-stationarity, because the non-stationarity is because of the receiver's receiving of the signal. So that makes the difference between if you're treating it as a policy or do you want it to treat it separately as a signaling scheme. So should I move on? Yeah.
I mean, I can think of other situations where agent take an action that also uses second agent, just like saying now the signal will influence the other agent that brings some non-stationarity, but isn't that actually what happens?
Yeah, that's a great question. So that's actually what is happening in multi-agent. So, but we haven't seen previous work that are exactly describing this. So we're trying to just derive, well, in a different work, we're just trying to derive what is going to be this effect. So basically, agent 1's action do have influence on agent 2's action, or agent 2's policy in general. So the gradient of agent 2 actually chain through agent 1's policy, which in turn chain through agent 2's policy, which in turn chain through agent 1's policy. So it's actually a gradient chain, but in a recursion version of it, to put it into the general form. So if you're treating action like these, then you don't need to just put it like signaling stuff, but previous work in general doesn't treat it as basically they cut the chain. They just only consider the policy gradient with respect to, well, chaining through only their own policy. Yes. Yes.
I'm a little unclear about the setting still. I don't know if you have further slides on that. Actually, like you have a set of agents, and in this set of agents, there is like one sender and multiple receivers, right?
Yeah.
And there is communication amongst all of them.
Oh, okay.
Yeah, and all of them, yeah, so there's communication amongst, communication amongst all of them, and the communication is free, or there is a budget, or
Yeah.
like, what is that?
Yeah, so short answer to your second question, communication are absolutely free. We don't consider the cost. And to your first question, it's actually a very complicated question, because when you send a message, there are multiple different ways of sending the message. You announce it publicly, or you send it privately to each of the agents. And then after that, it makes a difference of, do they make decisions individually, independently, or do they form an equilibrium among the receivers? So in this work, we're only talking about the easiest setting, which is they just act individually, independently, and you're sending everything in private.
Okay, so the sender has only one action, or what's the action space of all these? The sender has a bunch of actions, including action.
Yeah, so the sender has only a signaling scheme, so it can send signal. It can choose what signal to send.
Okay, what signal each receive?
Yeah.
Okay.
And if you want, the sender could also have an environmental action, which will be like the sender is also a player in the environment. That will be okay.
Okay, and the receivers communicate amongst each other?
No. Yeah. So if they do, it's going to be a more complicated side. It is investigated in information design, but not really in learning context yet.
And okay, can you also clarify the rotations? The bold A represents the joint action of all agents. Is that correct? And
Yes.
represents the global state.
S represents the global state.
Global state.
Yeah.
What is the bold O?
Bodo represents the vector of each agent's observation.
Okay. And which has, so all agents have access to capital, sorry, all agents have access to S?
Only the sender. Only the sender. So it's information advantage.
Okay. And what is sigma?
You mean sigma?
Yeah.
Yeah, that's the signal.
Sigma.
That's the signal that the sender sends. So basically, pi is the receiver's policy. It's depending on their own observation, which is local observation, plus the signal they receive.
Okay. And what is psi? The next equation.
Psi? I didn't see psi. Oh, it's phi. Yeah, it's the signaling scheme. It's the function that maps from the state to the signal, the sender's signaling function. And eta is this parameter.
So going forward, those requests on the chat, you simply question.
Oh.
Yeah, simply clarifying, but
Yeah, sure. Actually see the chat on Zoom. Yeah. I was trying to just clarify some notation. Oops. Yeah, so we talk about the obedience constraints now. So when we say something, we want our opponent to listen. We don't want them to just ignore us. So that's why we need the obedience constraints. We need the message to be better for them, to be plausible for them, under the very Bayesian posterior that is induced by this very message. So it's very similar to the obedience constraint of the information design case. We're just trying to have this posterior that is induced by the signal. And under this posterior, we wanted the expectation of the signal we are sending, which is the expected utility under the signal we're sending here, sigma, to be the best among all possible signals. So it's for all sigma and sigma prime. So this is the extended version of the obedience constraint that we put it into RL case. So basically, it used to be the prior, it's now the occupancy measure in RL. It used to be the signaling scheme, it's still the signaling scheme. And it's the utility and the utility. So, but there's actually one funny thing that it gives some insights to algorithmic game theory. So previously, when we are talking about information design, the linear program formulation, we have these phi or whatsoever signaling scheme. It's trying to send a distribution over actions, actions of the receivers. So in other words, it's trying to suggest actions of the receiver. Or we can say the professor is trying to suggest the HR, like you take this student, you don't take this student, instead of writing a long letter describing all of the quality and stuff of the student. So that is actually what the algorithms in game theory they like. They say, hey, I have this so-called information revelation. I wanted to use as simple signaling scheme as possible. I wanted to use very simple signaling scheme. I wanted to use as little signals as possible, making this space as small as possible. So making the computational time as small as possible. And in learning, we turn out this RL algorithm and we are saying the opposite. We're saying, no, don't do information revelation. We wanted to use as much information as possible. We wanted to use a larger informational space and to make it more complicated. Now, instead of suggesting actions directly, well, there are actions. Instead of suggesting actions here directly, we put a signal. We put a signal that just contains information and lets the receiver to do their own decision. What is the reason of this? So to talk about this, we have to revisit the commitment assumption. So our the strategy of the signaling scheme committed, or is it through an interaction, a long-term interaction between the sender and the receiver? If it is the later, we actually wanted this signaling scheme to be more robust in the sense that when it's run, it's still somewhat informational and somewhat useful. So they can start building respect. The receiver can start using the information instead of just ignoring it. So consider if what's going to happen if we're using suggesting action, if we're maximizing the information revelation, it's going to be these signaling schemes that say you do this action, you do that action, and it's sort of one of dictatorship. And this one of dictatorship will result in that through a long-term interaction, the receiver just ignores everything and the sender just sends arbitrary things. So it's a little bit of insights that is just giving the opposite to what information design area are doing. So moving on, we're going to have this constraint optimization. We're going to just maximize the utility of the sender subject to the obedience constraint. And there are many ways to solve constraint optimization. Lagrangian method is one of them. We also tried dual gradient descent, but it wasn't performed as well. But anyway, like there are many methods to do that. Yeah, so yeah, sure.
So is it fair to say that I guess the constraint helps ensure that perhaps action select something and have to try explore like what the effect is, like if I did not have this constraint, and I was simply classic RL, I was just trying to maximize my, I mean, it feels like in the long run, I should eventually learn that some actions to like the other agent understanding my signal at the right and what I hope that to and other actions that would just take longer, essentially explore and figure this out. So this is the right.
Yeah. So great question. So yeah. So Pascal was asking like, so what's gonna happen if I don't put this obedience constraint? If I just let them to learn without this kind of constraint, can they eventually figure it out that? So hey, when the sender sends information, I should send something that is very useful, and the receiver should respect this information. So in our experiment, we find out that it's the opposite, because this game has like many equilibriums. And the equilibrium of what Pascal said is one of them, yes, but there it's actually more fragile that represents a smaller part of the space. So there are more common, more trivial equilibrium that the sender just sent arbitrary non-useful things, and the receiver just simply ignores it, which forms another equilibrium that is much more stable. Like it's much more harder to deviate from that. So if you just let them do whatever using RL, using this self-iterational long-term utility objective training, they're more likely to converge to this trivial equilibrium. And when I say more likely, I guess something like 1 out of 20 Cs is gonna have some succeed, but 19 out of 20 are gonna fail. Yeah.
Actually, it would be great to have like a small discussion on this connection to some other model works in the past. I find like the things that you're describing is common in an algorithm like dial, differentiable inter-agent dial. And I think there are also commonalities to something like Lola. So you have like this is like a way of looking at it. One in Lola where every agent's actions influence on other agents is kind of differentiated across the joint policy space. And then in dial, it's about like how the communication impacts agents' actions across the entire set of cooperative agents. So I see that you're doing mixed motive, which is different cooperative agents in the other cases, but it would be nice to have a connection. Maybe you have on the slide on that. Can you comment on it?
Yeah, sure. So Jerome was asking like there are obviously famous works like Lola, Dial, in multidirectional, also what is the connection between them. So if we put this into Marl context completely, it's going to be a mixed motive communication in Marl. That's going to be the setting of it. So Dial is fully cooperative. And if we compare with Lola, Lola is going to be more on the receiver side. It's like when you receive information, or passively when you observe the action from other agents, which is also receive information, what is the agent going to do? So when we are doing this kind of information design formulation, we put it into a Stackelberg game model, we are mostly on the sender side. So when we are talking about Stackelberg models, we're on the sender side, or say the principal side, and we talk about the incentive compatibility and stuff. So it's quite different from Lola. Lola is more on the receiver side.
So you're actually modeling this as a turn-based game instead of a simultaneous game of games.
Yeah, it's yes. So Shriram was asking if it's turn-based or simultaneous. So in our case, it's going to be turn-based. So sender moves first and receiver moves second. But the only difference is that when sender moves, is not moving with signal, is moving with committing a signaling scheme. So, and once that's committed, it can no longer be changed. It can be stochastic, of course, but it can no longer be changed. Yeah. So yeah, that's our method, and can introduce a little bit of experiments. So, well, this is the recommendation letter experiment that a professor is trying to get these 2^3 minus 2^3 epsilon utility, and it does. So if we're comparing our method, which is SGOC, SG represents signal ingredient, and OC represents obedience constraint, you see that it's outperforming these non-OC version of methods, like say just signal ingredient, just policy gradient, just dial. It's pretty much better. It's going to be the same as policy gradient with obedience constraint. And well, obviously it outperforms other methods like dial because it's correctly recognizing that it's a mixed motif case, while dial is just mostly on cooperative case. And we also observed that it performs literally the same as PGOs. So, well, which is the question Pascal asked, if you just run policy gradient, what's going to happen? Well, in recommendation ladder, it's going to be the same. Nothing's going to happen because in recommendation ladder, it's one-step game. There's no non-stationarity. There's no trajectory generation. So you don't need to chain through the receiver's policy. And if you chain through that, it's nothing. It's a zero. So that's the experiments on recommendation ladder. And we see a little bit of funny things. Let's say there's a signaling scheme. So the professor writes 1 and 0 to represent good and bad students. So do you think 1 is for good or 1 is for bad? And on the other side, 0 is for good or 0 is for bad. So there's a symmetricity. So in some random Cs, you get a signaling scheme where 1 represents good students and 0 represents bad students. And in some random Cs, you get the opposite. 0 is for good and 1 is for bad. So it's actually concluding that when we train this, if we train a pair of sender and receiver, they work with each other, but not other pairs of senders and receivers. So a general case, a more general setting that motivates real-world applications is that can we train something that is off belief, which is saying that can we have a signaling scheme that works in general, doesn't have to be working only for the receiver is training with. So a little bit more of experiments is on the reaching goals, which is we have a few, we have a grid road, we have some agents. So we have the blue square as the receiver, which is trying to reach out for goals. And we have 2 goals. We have green, we have red. So some goals are good for receivers, some goals are good for senders. And we assume the information advantage that the sender can see everything and the receiver is blind. So the sender is trying to send information to guide the receiver to eat, well, mostly the sender's goal, but occasionally it has to be the receiver's goal as well. Otherwise, we don't have obedience constraint. Otherwise, it's not incentive compatible. So, well, in the experiments, we're seeing that this time, our proposed method is probably much better than previous ones. We have this SGOC that quite outperforms previous methods like policy gradient OC or dial or policy gradient without OC. So the first figure represents the sender's reward. And if we look into the social welfare, the third figure, it's also improving. So it doesn't have to be just the sender's reward, but also the social welfare. So, and in general, one may ask like, hey, this sender is so selfish. It's trying to maximize its own reward. What's going to happen that it's just trying to exploit the receiver? So the answer is that this reward, selfish, is in the RL sense, is the reward. So we can define it in other ways. So how about we define the reward of the sender as the social welfare? Is it going to maximize the social welfare? The answer is yes. So it's actually, by our definition, to what sense, to what objective it's being selfish. So I guess that's almost all of it. So we can have finally a more like an ablation of different observations of the receiver. So sometimes we have the receiver to be blind. Sometimes we have the receiver to can see a small neighboring hood, like 3x3 neighboring hood. So which agrees to our expectation that when the receiver has less information, our information design is more powerful because we have more information advantage. And when the receiver can see more information, the information advantage is less, and we get more reward through this information design. So some future works are, one is the figure we showed that it could be partial observability of the sender. Probably we don't get more theoretical results as signaling gradient lemma, but we may get more practical algorithms. And we can consider hypergradient, which is the gradient through the update of the policy, which is not included in this work yet. And we can consider multiple sender, which is a more complicated Stackelberg game setting where we have multiple principles. Yeah, so that's all of my talk, and thank you very much for coming. Any question are very welcome. Yes, yes.
Yeah, so just as a follow-up with respect to the last future point on sampling. So I guess for the case of recommendations, so I guess if there are several professors who make recommendations, one is like create following the strategy that describe it, then to a slide, probably half of the time, respect to the advanced students, and then another professor never lies. He recommends it to, then feels to me that in this case, I guess the receiver would eventually just professor never lies. Is this a right analysis? And then it's the case where by having multiple senders, now suddenly there's competition between them. The receiver is in a better position to like just take recommendations from two senders.
Yeah. The receiver know which professor is honest.
Yeah. So
yeah, that's
a very great question. So Pascal was asking if we have multiple senders, say multiple professors writing letters, and then they sort of form a competition, right? Like some professors going to be more honest, and then the HR trusts the more honest professor. So this is exactly the case. So I'm gonna give two examples. One example is the court. So you have two lawyers on opposite sides, and you have a judge. So what's going to happen for this information design on a court is that lawyer one reveals some information, and then to compete with this, lawyer two reveals more information, and then lawyer one reveals even more information, and then lawyer two reveals even more information, and so on and so forth. So their equilibrium is that they just reveal all information. So this is the case of the equilibrium. So if they move on the same time, the equilibrium is that they are very honest. So this is one example. The other example is that, Pascal, you're going to buy something for you. So you go to a shopping mall. There are two shops. So you're going to go to shop one, you're going to go to shop two to buy this. And the salesperson and you form a relationship of information design. They have informational advantage and they have a mixed motivity. So what's going to happen is that when you go to shop one, they're aware that, hey, I have an information design relationship with you, but there's a second shop. So what they're trying to do is that, one, they try to maximize their utility. Two, they try to persuade you, which is the obedience constraint. And three, they try to let the next persuader to not change your decision. So there's one more constraint compared with the one sender case. So this is probably a more learning, well, a case that is more suitable for learning, which is the sequential case instead of the equilibrium case. Yeah, thank you for the question. Any other questions? Yeah.
So how exactly is the reward function here being designed? Like now I understand that in the model context, it's normal to have a reward function that is conditioned on the joint activities. So it depends on the actions of every agent in the environment. So for the center is sending a signal, and now does the returns, like this is a turn-based game, the center is sending a signal. Does the reward function of the sender depend on how much the receivers trust the signal of the sender, or is there some other metric being used?
Yeah, great question. So Shriram was asking, like, because there's a signal being respected or not, and does the utility of the sender depends on how this is respected. So in the goal, or you can see that in the evaluation, the answer is no. Doesn't matter if it's respected. It's just pure utilitarian, pure selfish. Just consider the final utility. So, but in the optimization, if we put it into this Lagrangian form, so you can see the second term of this Lagrangian is actually how the signaling scheme is trusted. This describes how it is trusted by the receiver. So in the optimization, yes, but in the final objective and the evaluation, no. So it's more like a tool to achieve this.
So does the sender get rewards as long as it is sending a signal, or so for the games that you had in the experiments, maybe the professor writing recommendation letter. So the reward of the professor is based on this letter being written, or
yeah. So Shriram is asking, like, how is the reward defined in this recommendation letter example. So it's literally the numerical like reward we introduced. So if one student gets hired, then one. Yeah, basically that's it. So in the evaluation, we no longer consider like obedience and other stuffs. It's more like a tool to achieve just the utility.
and maybe one solution for the future work is it might be interesting to think about like the noise in the communication process.
Could you repeat what's of the
communication?
Oh, noise.
Yeah, so especially there are two types of communication that is common in model, the ones that you mentioned. One is broadcast communication, where you simply broadcast the information and anybody can listen to that information. Another is private communication.
Mm-hmm.
So especially if you're looking at the broadcast perspective, there's always some noise associated with the communication that is being sent out.
Mm-hmm.
So it may be good to maybe consider that also. So.
Yeah, exactly. So Shriram is suggesting that we consider noise in the communication channel. So which is actually whenever there are informational advantage and obviously mixed motive. So you have information advantage, you have to protect such information, which means your signaling scheme has to be stochastic. So this stochasticity usually entangles with the stochasticity of the messaging channel. Which makes it sort of entangled noise, which is a bit complicated. But yes, that's exactly one thing that should be incorporated in the future.
You have a question?
Yeah, we have a question on Zoom. So can the communication be masked, like in masked agents, where some actions are masked? Can this be done with this approach? Sorry, I didn't really understand. What do you mean, masked the communication?
Yeah, I think what the question means is that you see there are certain reinforcement learning environments where all actions are not available in all states, right? So some actions would be masked, which means that those actions cannot be taken in that state.
Oh,
And in the same way, can you say communication can be masked in the sense that certain communication signals are not available?
yeah. Now I understand the question. I don't have an immediate answer, but I feel like there's nothing preventing it. It's similar to like if you have an action space that depends on the state. So basically, signaling gradient lemma is derived with very similar techniques. So yeah, I don't see it's prevented, but I don't have an immediate proof at the moment. I think the answer is yes. Yeah.
So I have another question. So I guess back to the comparison of but with alternative constraint versus planning. So I guess you make that constraint on that are undesirable. Now, from an optimization perspective, is it possible to analyze two optimization problems and show theoretically that yes, there aren't pure optimal, just one optimal once you introduce that constraint that is under the right properties that introduce that constraint. I guess some or all of that.
Yeah, that's a great question. So Pascal was saying like there are obviously more than one equilibriums, and can we actually characterize what are the equilibriums in the optimization and what are other non-equilibrium local optima in the optimization, and then how can we get rid of it, or just setting up certain constraints that it doesn't trap into that. So we actually tried it a little bit, mostly empirically. Just to see that if we just if we just try very different initialization, what's going to happen for this optimization. One thing we tried is that, say, I train a pair of agents, one sender and one receiver. So the sender actually becomes like more honest, more like subtle in its information. It's a good signaling scheme. And then I let this very well-trained sender to be retrained with an untrained receiver. So I tried this. So what I wanted to observe is that can this well-trained sender to make this untrained receiver trained, so make them trust them, make them respect them, which is something we wanted to just to make it more stable. So if this is possible, we can make it a multi-stage training, like train one stage, they become a little bit more subtle, making sense signals and stuff. So empirically it's possible, but more than that, like analytically, we don't have more results on this yet. Yeah, but like basically the landscape of this optimization is definitely interesting.
Thank you for the question. Yeah, can I just ask one quick question? Do we assume that the sender can access all the information about the receivers, like the observation of the receivers, the policies of the receivers, and all the information about the receivers is available to the sender? Because I think your lemma is being separate.
Yeah, so let me repeat Shriram's question. So in signaling gradient lemma, this is from the perspective of the sender. It's actually using the receiver's policy. So this is an assumption that it has access to it, but it's similar to just multi-agent PPO. We can just estimate this instead. We also tried this. We don't find much difference actually. So you can just, the sender can just maintain a neural network that basically copies whatever the receiver does.
So if you do that, then isn't that the same as the stochastic policy gradient theorem from Lowe et al.?
What is the last term from what?
From Lowe et al., that is the multi-agent actor critique.
Oh, I actually don't know what is Lowe.
Lowe et al. Is the name of the author. Yeah, Lowe is the name. So the paper is multi-agent actor critique for mixed cooperative competitive environments.
I don't know that one either. Yeah, maybe you send me the paper. Yeah, I'll take a look.
So there's a follow-up question.
Yeah, the question is asking with the masking question, certain communication has to appear in order to activate another one. Certain communication has to appear in order to activate another one. Could be a conditional constraint to that. Okay, I didn't understand the second, but the first one is if certain communication needs to activate the second one. I don't think our formulation is good into this. So if you need one communication to activate, to even activate another one, which means your communication has to be depending on like your communication, which means the communication is no longer a mapping from the state to the distribution of actions, which in this case probably our setting disagrees with this. It doesn't have the capacity. So if we want this kind of capacity, we need the signaling scheme to be based on the trajectory instead of the action. So I guess the short answer is no, we cannot do that at the moment.
Maybe as a follow-up, so I guess instead of having the mapping from states to signal, and then now by
Yeah, so Pascal is asking like, so signaling scheme, I guess you mean signaling scheme. It's from state to distribution of actions. And then can we have it to be from belief to distribution of action? So actually, if the sender is in a partially observable environment, which we also tried, it doesn't even have access to the state. So it has to be belief. It has to maintain a belief of the state and then just use this belief to whatever the signaling generation. So it's similar to using policy gradient in just POMDP. So if you don't have full observation, the policy gradient doesn't really work. It's no longer true, but we still have to use it just by replacing these state with a belief and getting this belief through other numerical methods, such as just neural network, recurrent neural network. Yeah, so if we don't have state, yeah, that has to be.
There's another question.
Yeah, in the experiment, the receiver appears to be exploited. So because it's lower reward compared to dial, it seems to be trapped to in a local optimum, even though theoretically it has the ability to influence the sender's reactions and negotiation better outcomes over the long term. Yeah, this is a great question. So it's basically saying, so you have professor, you have HR, you have this professor very strategically find out this information, this design strategy. So can the HR do this? So you read a good letter, I have more utility to respect your letter, but I just don't. And in the sense that I wanted you to read even more informational letter. So like through a long-term interaction, this is kind of just some kind of behavior that forces the sender to be even more honest. So it is possible. When we did the experiments, we were worrying about, does it emerge with reinforcement learning? Because theoretically it could be, because reinforcement learning considers long-term goal. But at least when we have like all these experiments, it never happens numerically. So yeah, that's what we know so far, but it is possible if we consider this long-term interaction. So actually, when we list the commitment assumption, this is something inevitable that has to be considered. It's probably in future works.
Any other questions? All right, so let's thank Baoxiang.
Thank you very much. I just stop sharing.